before I explain to you how we decouple carbon-13 NMR, which we do normally, I'm going to explain how the coupling would occur between the hydrogen, proton, and carbon-13 atoms if we did not decouple. So here it is. Here. Let's look at the bromoethane we looked at before. And if we run the NMR spectrum as a proton decoupled carbon-13 NMR spectrum, you just get two peaks like that. That's what we'll normally see. So I got signal 1 more downfield, signal 2 more upfield, about 17. This one's about 27 or so, and they correspond to the carbon with the bromine on it. It's de-shielding that carbon a little bit. It's a little more downfield, and then the carbon 2 here, more upfield. Here's what the spectrum looks like if we allow the hydrogen atoms to couple. So it looks like a triplet of quartets, so 3 quartets, or a quartet of triplets, 4 triplets. Let's explain what's going on there. So that would be signal 1 proton coupled, that's signal 2 proton coupled. So signal 1 for this carbon here, it has 2 hydrogens directly attached to it, and these 2 hydrogens will couple that carbon strongly because they're so close, they're attached. And this gives them what I'm calling a strong triplet flavor. So this is what I mean. So there's going to be a portion here, a portion here, and a portion here. So the biggest coupling is a triplet there. I don't want to say quartet because I don't want to confuse you, but it's a quartet, 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 right? So that's from the neighbors that are real close. And then carbon number 1, it also is coupled by these hydrogens that are further away. And those carbons, they couple, these hydrogens, the purple hydrogens, they couple carbon 1 weakly compared to the red ones that are directly attached to it. So what they do is they add a little bit of quartet flavor. So you can see each of these 3 parts are split into quartets by the further away hydrogens. So that's why you have like a quartet here. And then this one has a quartet flavor, quartet flavor. I just point arrows at one of them as a representative. All right, now let's look at, now I think you're getting good at the n+1 rule. When you have 2 neighbors, you're a triplet, 3 neighbors, you're a quartet. Let's see what's causing that n+1 rule. The hydrogens attached to the carbons, all these hydrogens, they can be in either their alpha or their beta spin states. Let's draw out all the combinations of alpha and beta spin states for the 2 closer hydrogens first. So we're going to look at this, we're going to focus in on signal 1, and we're going to look first at the 2 hydrogens directly attached to that carbon. So these 2 hydrogens, they can be both in the alpha spin state. That's one combination, right? Because each of these hydrogens can be alpha or beta, so there's a chance that both are alpha. Or there's a chance that one's beta and one's alpha. And say I chose that wedged out one to be beta just randomly. It could have been that the wedged out one in this configuration, it's alpha, and the back one is beta. So I got that combo. And there's one more combo. Can you think of what it is? I bet you guessed right. Beta and beta. So that's all the possible combinations of the red neighbors that are closer. So that's 4 possible combinations for those 2 hydrogens. But wait a second, these 2 neighbors are supposed to couple n+1. They're supposed to couple 2 + 1 3 times. Should be this configuration is supposed to lead to a triplet. But why 4 things? How could 4 things make a triplet? Well, the 2 middle ones are the same energy. They're equivalent. Having 1 beta, 1 alpha, or 1 alpha, 1 beta for hydrogens that are equivalent, they're going to be the same. So you're going to get this configuration. 2 alpha neighbors will give you one of the parts of the triplet. And then when you have an alpha and a beta part, alpha and beta combo, that'll give you another part of the triplet. And then lastly, the beta gives you gives you a third part of the triplet. And this triplet, if you remember, it's taller in the middle. So, looks like these 2 cause the middle part of the triplet. But let's go ahead and look at that closer. So here's the combo summary real quick. We got alpha. Alpha is one possibility. Beta alpha. alpha beta or beta beta. All right, so there's 3 unique things there. The alpha alpha combo, it causes the more downfield part of this triplet. And the beta alpha and the alpha beta, those two, they cause the taller, more area middle part. Isn't that cool? And then the beta beta causes the right side of it. Awesome, huh? Hope you're liking it. I think this stuff is cool. Okay, now we'll repeat it now for the 3 hydrogens further away. So we're still focused on signal 1, but we're looking at that long range coupling. So I'm still going to look at this guy's signal, but I'm going to consider these further away hydrogen neighbors. So they can all be alpha. Easy, right? Just like before, we're just going to kind of go through the combos. So all alpha, but what about if I just have 1 beta? Let's say I put the 1 beta there, and then I got 2 alphas on the other ones. That 1 beta, it could be this one in the plane, the line hydrogen here, the one that's in the plane. Or it could have been that beta was on the dashed back there. Or there's a third possibility, the single beta is on the wedged, right? So that's all the combos of just having 1 beta and 2 alpha. But there's more. What if we have 2 betas and only 1 alpha? That 1 alpha can be in the plane there, or that 1 alpha could be dashed back. 2 betas and an alpha. Or finally, the 1 alpha could be wedged. So there's 3 combos of 1 alpha, 2 betas. And there's one more possibility for this 3 hydrogen neighbor set. Do you know what it is? I bet you guessed it. Beta, beta, beta. There we go. So there's a lot of combos here. 3 neighbors can have 8 combinations of alpha beta. So this is even more nuts than before. So when you have 3 neighbors, n+1 rule says you should create a quartet. So 3 neighbors should create 4 splittings. How could 8 combos create 4 splittings? I'll tell you what. Once again, we have some combos that are equivalent. So for example, the alpha alpha alpha, that's unique. Nobody else is all alpha. But what about when you have just 1 beta and 2 alpha, and the 1 beta is just in the 3 positions? Oh, those are all the same. Cool, huh? And then over here we have a single alpha and 2 betas. Those are all the same. And finally, that all beta, 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 they're equivalent. So how many groups do we have here? 1, 2, 3, 4. Awesome. 3 neighbors, 4 groups, quartet. And if you remember, a quartet is taller in the middle. And that's what we see here, huh? I mean, sorry, we're looking at this guy now. We're looking at each of these quartets. And that's what we see there. So we see all alpha all the time. And then we've got a combo of 1 beta, 2 alphas. Our other combo was 1 alpha, 2 betas. And finally, beta, beta, beta. All beta. It's all we know. So let's see how these work out. The alpha combos cause the most downfield part of each signal's quartet. And then when you have the 1 beta and 2 alphas, they're the tall middle one, that's more downfield. And then when you have just 1 alpha and 2 betas, then you're the taller middle, but to the right, more upfield. And finally, the all beta, 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 beta. I said that too. I got too excited about my betas. Yeah. Beta, beta, beta. That's the most upfield of the quartet. So that's what happens. And then this quartet, the same thing. Like these guys cause the left side. The 1 beta causes that. This 1 alpha, all betas. We got the same on this guy. Pretty cool, huh? So I'll finish with signal 2. We haven't really addressed signal 2. We were focusing on signal 1. I'm going to do it quicker, and hopefully I'll do it slightly different, and maybe it'll make it sink in more for you. So I'm looking at signal 2 here, not signal 1. So it has hydrogens attached to. Those are the hydrogens attached. Let's look at the hydrogens attached to carbon 2 directly. There's 3 of them, huh? And those 3 hydrogens are closer to signal 2, so they're going to couple stronger and have, so that that signal should have a strong quartet flavor. And that's what we got, huh? See the four main parts there, the four triplets. And then signal 2 also has hydrogens that affect it that are attached to the other carbon further away. So those further away carbons for signal 2's carbon, they give you weaker coupling because they're further away. And that adds like a triplet flavor to each part. So see how that we got a triplet on each of these. The larger coupled things are each split into triplets. So that's why we get the quartet of triplets. Pretty nice, right? So let's do the alphas and betas. I'm going to do this quicker though. So we're focusing on signal 2 there. 3 neighbors close up. What are the combos you can have? Instead of drawing up this molecule over and over, I'll just say I could have all 3 of these be alpha, alpha, alpha. That's one combo. Or I can have a combo where, like, say this one's beta, the other 2 are alpha. Then I could have, this one's alpha and the middle one's beta there. And then I can have the combo where the right side is beta. Okay, those are all combos. And then I can have alpha here and 2 betas. And then my single alpha could be in the middle and then, or on the outside, right? And finally, what's the last combo possible? Beta, beta, beta. Okay, so 3 neighbors should be causing a quartet. How's that going to work with all these combos? Because that is unique. These all alpha all the time. And then this one, these are all unique because they just have 1 beta. And then these ones are unique because they have just 1 alpha. And then this one, of course, team beta, beta all day. That's how we roll. All right, a strong quartet flavor for this. When you have this causes a strong quartet flavor because these 3 hydrogens are directly attached to carbon 2's carbon, or signal 2's carbon. Okay, here it is, signal 2. So we've got the strong quartet flavor. Nice, huh? And then now we'll focus on the further hydrogens. So there's only 2 of those. They can both be alpha, or one can be beta. Like say this one's beta, the wedged and the dashed is alpha. Or the opposite, wedged is alpha, dashed is beta. And then finally, beta, beta. Easy, huh? 2 neighbors. So we have those are unique, all alpha all the time. And then you have, 1 of each. Those 2 are unique. And finally, team beta, beta. That's a beta all day. So this, since those 2 neighbors, for this carbon, those 2 neighbors are further away, they just give a hint of a triplet flavor. So we see that on each of the quartet parts. See those 3 there? And that's why we see the triplets here, here, here. And again, the all alphas is the more downfield. The combo, 1 alpha, 1 beta, taller in the middle. And the beta, beta farther upfield on the right there. And you got it. So that's why carbon-13 atomers are coupled by protons if we allow it. Next, I'll explain how we stop it from happening.